Hello everyone, welcome to another exciting lecture of digital signal processing. So in today's class, we are going to be doing a numerical on your fast Fourier transform using Radix to decimation in time algorithm. So in our previous class, we have seen what is a Radix to DIT and what is the need for your fast Fourier transform or your FFT. So in today's class, we will just see how we can solve this on a given sequence. So the sequence that I will be taking here is 11001100, and we are going to find the 8-point FFT for this, and then afterwards we are going to solve the 8-point inverse Fourier transform. So we're going to see these two numericals, and then you should be familiar with how to. It should be familiar for you on how to do this in your exams or whenever you need them. Good. So let me get started with my twiddle factor or my linear transformation W80, W81, W82 and W83. So these are the values I have, and I have computed these values using my scientific calculator or my Scilab. So you can get it using either Scilab or your calculator. So I got it to be as 1.7 minus 0.7 j minus j and minus 0.7 minus 0.7 j. So that much I need to do. I need to compute that using my calculator, but that is all I need to do. Suppose your question is to find an 8-point DFT using an ordinary method. So not using the fast Fourier transform that we are going to be seeing. If it is just using your ordinary method, you need 8 twiddle factors. You need this remaining twiddle factors, which is W84, W85, W86 and W87. And now those values I've written it as this, and I have not computed them. I have not done calculation for these values. What I used was the symmetry property, and that gives me my W84 is symmetrical with W80, which means my W84 is equal to minus W80. And similarly, my W85, W86 and W87 are symmetrical with 1, 2 and 3, the powers. Right, so I can write these other 4 values without needing to compute them in the exams or in your test or wherever you are using these. So you don't have to calculate each and every twiddle factor. Wherever possible, apply the property and get the values automatically as we have done here. Okay, so now going to our fast Fourier transform, I need to first study this sequence. So this is an 8-point sequence. So which means I have to decimate. I will have 3 stages of decimation. So I have to decompose this FFT, or I have to decimate this FFT 3 times to obtain the full representation of my Radix 2 decimation in time fast Fourier transform. Excellent. So now for my inverse, that is what I'm writing there. It's a bit for my inverse Fourier transform, and I'll come to that when I solve the inverse Fourier transform. So I can just tell you that my FFT and IFFT are very similar, exact to each other, the steps in terms of the steps, but the only difference is the Wn that we are using in FFT becomes the Wn conjugate, because the inverse Fourier transform is Wn minus, so that becomes a conjugate. The inverse becomes conjugate for my complex exponential, right? And then I have a scaling factor of 1 by n. So that is the only new things that I have for my inverse, which I have to do when I'm solving them. Now let us see how we do the forward Fourier transform. So in my forward Fourier transform, I have 1 1 0 0 1 1 0 0. This is my input sequence. So my input sequences are indexed in this manner. It is indexed in sequence from 0 to 7, as I've shown here. But this is not the index that we are using for our fast Fourier transform, is it? We are restructuring. We are doing a little restructuring at the beginning of the fast Fourier transform, and that restructuring is shown here. So I'm writing it as 0, 4, 2, 6. Those are my even group. Then 1, 5, 3, 7. Those are my odd group. So this restructuring is something you need to remember. This order, it has to be 0, 4, 2, 6, 1, 5, 3, 7. It should come like that. It should come like instant to your head when you're doing these problems in the exams. Good. Now I write the equivalent value, because, and also another thing is you write the index. You don't just see the question and you write what is 0 and what is 4. You write just below each of these values, you write the index like I have shown here, so that you don't go wrong when you write these index in your paper. Good. So x of 0 is 1, x of 4 is 1, then I have my x of 1 to be 1 and x of 5 to be 1 and rest of the values to be 0. Now let me get to my stage 1, which is what I'm doing here. So stage 1 grouping is between successive samples. So which means I'm taking my first two samples 0 and 4, then 2 and 6, 1 and 5, and 3 and 7. So I'm grouping between successive samples, and my twiddle factor is plus or minus W80. So for my stage 1, my twiddle factor is plus or minus W80, and that is exactly what I'm doing. And always a reminder or a thing, you can remember this: if the plus comes first in all these stages, wherever you are using a plus and it's having an equivalent pair, because of the symmetry it will have a minus. So there will be always equal number of plus and minus in your stages, and also the plus comes first, the plus comes above the minus, and that is what your stage 1 has shown here. Alright, so this is 1 plus W801, 1 minus W800, 0 plus, 0 minus, 1 plus, 1 minus, 0 plus. So just I have written, and that output is coming out to be 2000200. And this values I'm carrying it forward, I'm taking it to my stage 2. At stage 2 there is no restructuring in my index, I'm writing it as it is, and then I'm doing the pairing and applying the twiddle factors or my linear transformation multipliers. So how do I do the grouping in my stage 2? I am taking every other sample and grouping my first and third, second and fourth, good, my fourth with my sixth, and my fifth with my seventh. So I am taking every other sample and or every alternate sample for my grouping, and my twiddle factors or my linear transformation multiple is going to be plus or minus W80 and plus or minus W82, right? And as you can see, my plus comes first, followed by my minus, and I have equal number of pluses and minus. So now I do this computation after my grouping, and I get the outputs to be 2020 and then 2020. So this is the output of my stage 2, and I'm going to be carrying this values to my stage 3. Good. So just you have to know these twiddle factors, and you have to know how to group them, and then you won't go wrong. So this is a relatively simple computation in terms of the values, because there are equal, I have half the sequences consisting of zeros, but nevertheless, the important thing is you should not go wrong with these steps that you do. The other thing is left to you, and how you compute or how you use the calculators to solve this. But the steps are more important for the marks and also for your understanding. Good. So next I'm doing my stage 3. So I've written my sequence output 20202020, and now how I'm going to be doing, what is the grouping that I'm going to use in my stage 3. In my stage 3 I am grouping my first value or first sample with my fifth sample. So what is this grouping means, why it is like so far away from one another? So it is because if you look at the input side, my first 4 samples or the first 4 are my even group, and the next 4 or the last 4 is my odd group. So for my stage 3, if you look closely, what's happening is I take my first even and I pair it with my first odd. Good. Then I take my second even and I pair it with my second odd. Then I take my third even, then I pair it with my third odd, and my fourth even with my fourth odd. So that is exactly what's going on in your stage 3. And then you have your twiddle factors to be plus or minus W80, plus or minus W81, plus or minus W82, and plus or minus W83. And the pluses come before the minus. You have 4 plus and 4 minus as shown here. And the output that I get is now in sequence. So there is no need for doing any restructuring in indexing. when it comes to your output, so if you see you have x0, x1, x2, x3, x4, x5, x6, x7, they are in sequence, the sequence indexing, so there's no change there, and that is, you write the output as you get, and that is your fast Fourier transform for 11001100. So let me complete the butterfly representation because I have to show you, right? So this is a butterfly DIT, butterfly decimation in time representation and solution for my fast Fourier transform. So the butterfly is complete with my X between this paired group. So the groups that I am pairing, I am just connecting them with two diagonal lines or an X, whatever you like to call them, and that completes my butterfly diagram. So this is how you do your Fourier transform, a fast Fourier transform in the DIT method. Good. So why it is fast, we are coming to that. So we are coming to the computational part soon. Next, what I'm going to do is, I'm not going to stop there. So I have done my FFT for an input sequence. Now I'm going to take this FFT values, right? And I'm going to find the IFFT. I'm going to do the inverse FFT for this values. And then I have to get back my original sequence, which is 11001100, right? So I want to show you how to do the inverse DIT or inverse decimation in time FFT. Then just so that you can do any of this in the if needed, it's very simple. There's only slight alteration between a forward Fourier transform and an inverse Fourier transform, and that is what I'm going to be showing to you. So the first difference is there is a scaling of 1 by n. So if you see the formula for my Fourier transform, it is xn is equal to wn xn, and for inverse Fourier transform, it is 1 by n wn conjugate xn. Right, so the change is your twiddle factor or your linear transformation multiple w is now used as wn conjugate in your inverse Fourier transform. And then you have a common multiple of 1 by n, where n is the length of your sequence. So in this case, my sequence, my Fourier is given, the question is given to be an 8-point sequence, so which means my n is equal to 8. Good. Then the number of levels are going to be the same, right? It is log 2 8 equal to 3. But for any question, it is needed to compute this, and then I'm getting that to be 3. And now my inverse Fourier formula is equal to 1 by n wn conjugate xn. So let me just write these conjugate values for you, because many of you go wrong with this conjugate and symmetry. So the conjugate values, what we do. So when I write wn conjugate, what I'm going to do is I'm going to take my wn values, and wherever there is a j, right, there is that imaginary variable j, I am going to change the sign of that j. That is the only thing I'm going to do. I'm not going to change anything else in the values. What I'm going to do is wherever there is a j, I'm going to change its sign. So if I am seeing a plus j, I'm going to convert that into a minus j. I'm going to change it to a minus j. And if I'm seeing a minus j, I'm going to change it to plus j. And that is the only thing you need to do to find your conjugate. Good. So as we have seen, the 3 level of decomposition at the level 1 or the stage 3 towards the output, I had plus or minus W80, W81, W82 and W83. And then the middle level was plus or minus W80, W82, and towards the input side, towards the input sequence side, I had plus or minus W80. And now I'm going to write its complex conjugate. So for my inverse, I'm going to just use this conjugate, and these conjugate values are going to be W8 conjugate 0, W8 conjugate 1, and etc. All right. So now, like I said, how you find the complex conjugate by changing the sign of the imaginary variable j. Rest of the things are pretty much the same. The steps that we are going to use for stage 1, you're pairing successive samples, and your twiddle factors are plus or minus W8 conjugate 0. Then for stage 2, you are taking the every alternate sample or every other sample for grouping, and your twiddle factors are going to be plus or minus W8 conjugate 0 and plus or minus W8 conjugate 2. Then for stage 3 towards the output side, I'm going to have grouping between every first even and every first odd. So that is my first and fifth, my second and sixth, my third and seventh sample, and my fourth and my eighth sample. So if I have to number it, it's going to be in this manner. But if I have to say it in English, I can just say it is between my first even and first odd, second even and second odd, third even and third odd, and so on. So the critical factors for my stage 3 is plus or minus W8 conjugate 0, plus or minus W8 conjugate 1, and plus or minus W8 conjugate 2 and 3. Right, so this is your inverse DFT, and it is pretty straightforward. Let's get to it and let's do. So I'm writing the values of the conjugates, so I just write these in the boxes, and if you compare them with Wn, you can see that my minus j has become plus j and my plus j has become minus j. All right, so now the important thing is I start my inverse Fourier transform. Right, inverse Fourier transform using the decimation in time algorithm also starts with a restructuring of my indexing. So I see the index here, I am writing it as 04261537. I'm not writing it in sequence. So that is followed even in your inverse transform. And now I know what are these values that's given to me in my question, or that is taken from the fast Fourier transform output of my previous, that is a solution to the previous question, and I'm writing it here, my what is my x0, my x4, my x2 and x6, and this is done, and then I'm going to solve the different stages. So other things will look very similar to you, very familiar to you. And now what will happen is, this we can do up to 8 point on a paper. So I'm going to show how to do this 8 point, and then after this I'm going to show you how to do the 4 point, right, 4 point FFT and inverse FFT, and then I'm going to do the computational complexity. So I'm going to show you why these are considered to be faster than your ordinary DFTs, right? So let's just take a look on the computational aspect from this butterfly diagram I have right here. So if you just count the number of additions and multiplication I have for just one of these stages, so I'm doing the first stage where I'm grouping successive samples. You can see that I'm having around 1, 2, right, 3, 4. So if it is not a complex, so I'm just I think I'm having like 8 additions or subtractions and 8 multiplications. So that is what I'm having for one stage. So I'm just having like 8 multiplications if I just count it here, and then I have my 3 stage, which means I'm going to see some total of 24 multiplications, give or take. That is my rough calculation. It is not an accurate one, but I can just knowing that what's going to come in my stages, I can just tell that I'm looking at around 24 multiplications. But whether this is an improvement, so we saw for ordinary DFT, ordinary discrete Fourier transform, the number of multiplications was n square. So which means in this case, I'm having an 8 point sequence. So the number of multiplications is going to be 8 square or 64. Good. So that is a big reduction in the number. So here in my fast Fourier transform, I'm seeing only 8 per stage, and that's coming to 24 for the entire fast Fourier transform, which is, I'm saving up on 40 multiplicative steps, which was excess in my discrete Fourier transform. So you see the improvement, and that is just for my 8-bit. So let us say I'm having a bigger bit, I'm having a bigger FFT, I'm having a 256-bit Fourier transform, then 256 square, and whereas here it will be just the number of bits 256 into, right, it will be just 256 is what, 2 to the power of 8, so I can write it as that 256 plus 256 plus 256. So it is going to be 256 into 3, that is the number of multiplication for my Fourier, and the other one is going to be 256. But the difference is going, what I'm telling is, as we increase the size of my DFT signal, my difference or that multiplication, say, it's going to be big. The difference in comparison is going to be big, and your FFT is going to prove very effective and very efficient in terms of these computational complexity. So that is the advantage. I just wanted to talk about it a little bit because I am covering it up in the next lecture. I'm going to do this in about this computation. I have so, but I just thought, we have done the FFT and now the inverse FFT is pretty much the same. So I thought I'll just run this over for you so that it is known to you what is the advantage of doing this FFT for your um, like computation. Good. So now let us see the stage 2. So in my stage 2, I am having W8 conjugate 0 and W8 conjugate 2. Those are the twiddle factors and the pairing is between every other sample. All the things are the same, right? It's going to be just conjugate. I'm going to use the conjugate and then I'm just doing the same computation, and for my third stage it's going to be like first with the fourth sample or my first even with my first odd, and then I'm going to use the other four twiddle factors, and then I'm going to get I should be getting the output to be 11001100. So because I know that is the input, and what I did was I found the FFT for that input, and then I took that output and I'm doing the IFFT or the inverse FFT for that output. So I must be getting back my input. So let us see how that turns out to be. All right. So that is pretty much it. So this is your DIT, decimation in time algorithm for your fast Fourier transform. So your butterfly is when you put the diagonal line. So if you're saying questions, so I have seen some questions where they simply ask you to compute the twiddle factors or the linear transformation multiple for and 4 point, 8 point. I've seen this as interview questions. I've seen that to be asked in some of the service sector exams on FFT, computing the FFTs. So and mostly they give some questions which are easily solvable in quick time. So it's not going to take a lot of your time, and so it's not going to be intensive computation or calculation with your calculator. That is not what they intend. They just want to test how much of this concept you know. So it's very important because FFTs never, if you are in signal processing, then you are using FFT because you have all the filters. Because when I say digital signal processing, then that is nothing but your filters, right? We are using sound filters. We are using to enhance the sound. We are using to change the frequency, change the sound, add some bass, treble, equalizer, this amplifier. All this can be implemented and done as your DSP filters, and that is what your DSP filters are used for. It's either for filtering the signal to give better quality or to get rid of some noise or some kind of disturbance in your signals, and all the filters work with frequency. I can tell you that much. You almost, I would say, like 99% of the filters in the market are using your frequency designs. And when you have a frequency design, you must be using FFT at some stage of that filter. So I'm not telling your entire FIR or IIR filter, or the designs are based on FFT, but you are using FFT because the properties of FFT allows you to simplify the computations, reduce the number of multipliers and adders to a great extent. So you can't do without FFT if you are a signal processing guy. Good. So that is why these are important topics, and I'm sure that by explaining it twice or thrice in my lessons, this becomes very thorough to you. And now I'm doing the stage 3, the last stage, with my 4 twiddle factors, and the pairings are shown here. And that is going to give me my final IFFT or the inverse Fourier transform output. Or is that the final output that can we call that as our final inverse Fourier transform? Not yet, right? Because can you tell me why? I've still not done that 1 by n. So I am looking at doing my 1 by n, right? So that in this case, it's going to be 1 by 8. So this output that is coming out of my stage 3 has to be multiplied. So each and every value that are coming from here has to be multiplied with that scalar multiple 1 by 8. And that gives you your final output or the inverse Fourier transform output of 11001100. See, this is the sequence that I started with. So that sequence is given by 1100 1100, right? That was my starting sequence. Starting of this lecture was that, and I'm ending that lecture. I've taken the first fast Fourier transform, then I computed the inverse fast Fourier transform, and I've shown you what is the difference between fast Fourier transform and the inverse fast Fourier transform. And we did a little bit on discussion on the computational speed improvements using the fast Fourier transform. So that's it for this lecture. See you soon. Thank you.